Okay, so I'm live. Welcome, zero viewers. Today we are going to talk about GANs. So even though no one is watching, I'm still going to talk anyway. So what we're going to do today is we are going to write a bit about GANs. We are going to write a bit about GANs. Why can't I delete this? Move to trash. So why do I want to write about GANs? Because I think that if you can, like, writing is formalized thinking, right? So if you, I'm gonna make a new project here. I'm gonna name it maybe something like ML book. And I am going to take one of my old tech files and I'm going to copy it. It's going to take my old thesis file here. With all the packages in there already. Hey guys, good evening. So let's say it's a main ML book. So today we're going to write a bit about GANs. We're going to try and formalize our thinking. We're gonna formalize what we did in the past couple of days, and then if we are finished with that, we might do some other stuff, like more coding based. But I think that being able to write down what you mean and being able to follow along with those symbols is like half the hard part already. So this was the title of my thesis, measuring high frequency contagion in Hawk's jump diffusion models using particle filters. I tackled this problem and I had to do some tricks to get the right results, which was the key novelty. I don't know if you guys have any experience writing LaTeX, but I'm going to write this in LaTeX, and I will show you guys that writing in LaTeX can be very fast. It can be like extremely fast if you know what you're doing. So if you have any questions about how to write LaTeX, feel free to ask, because I really like hacking around in my productivity. I like hacking around in Vim and increasing my productivity. So today we're going to write about GANs. Actually, more in generality, we're going to write in general about machine learning, right? So the title is going to be machine learning. I have to add a bibliography at some point, which is, I guess, now. Yeah. All right, so let's compile that and see if it works. It does work, and we get a nice PDF here. Okay, so that's our base where we're going to start from. Machine learning. Okay, let's make that machine learning, because this is about machine learning, right? So let's start with the first section called GANs. Author, make title. So let's make title, of course. This is the bibliography. Then here we have the GAN chapter. So section GAN, or Generative Adversarial Networks, GANs. All right. So we are going to write about GAN. What is a GAN? How do we get it? How do we train it? If you guys have tuned in the first couple of streams, in the first stream, oh, that's also another thing I want to do. I want to give in my Twitch page, I want to make a quick kind of a summary of what we did, because this is the fourth stream already, and we spent the first stream doing neural networks. Then the second stream we did GANs. We started on GANs, and in the third stream we also started on GANs. And it turns out that even programming in the simplest of GANs that there is, like so the original one, already turns out to be quite difficult. So I'm going to open the file called refs here. I'm going to have to make a new file called refs, and it has to be a bib file, I think. So let's see, refs.bib. Okay, so that's empty. I need a ref file so I can get the references in here working, right? So let's see, refs. Gonna copy that, I'm gonna paste that here. And we're gonna start by going to Google Scholar and hey new viewer. And we're gonna start by looking up the original paper about GANs by Ian Goodfellow, 2014. Good evening, guys. Hope you guys are having a great evening. This paper has been cited 5,000 times. So then to cite this, we go here, we type, click here, and then we copy this. We click on BibTeX, and then we wait for it to load. We copy this, and then we paste it in our refs file. So I actually wrote a script for this, how to do this, but I can't find it anywhere. So now we can cite this using this keyword here, which we will, but I still haven't figured this out completely. So if I now type like cite and I compile this, I actually get question marks. Yes. And I know how to check, like I know how to fix this, but I'm not sure why my it's probably like the thing I'm compiling with. So this is my Vim configuration here, and then we go to PDF LaTeX. I have some compile. So any other compile? Yeah. So this is, so if I press Control T, I save the file. Then I type leader LL, which compiles it, but I think it doesn't compile it with like with BibTeX, because you need to compile it with a certain type of tag to get rid of these question marks here, which of course I know how to do, but I just haven't figured out how to get that properly working in let's see, text shops should be in here. I haven't found out how to properly do that with Vim. So what we're gonna do today is we're gonna write a bit about GANs. We're gonna formalize our thoughts, and we're going to get the bigger overview of what a GAN is, how to train it. If we have enough time, I might just start working on the code again, but I'm not sure because it's already quite late, and in the evening I know I'm not that sharp, but maybe I am because I'm streaming. But we'll see about that. So often when I'm coding at night, when I'm typing something at night, I put in more errors than good things. So let's see. So if we open this up in text shop as well, then we compile it with, I think, PDF LaTeX. And it gives a lot of errors, of course. And then it should resolve the citations here, such that we can cite it. Look, so now it has resolved the citation, and we can cite it. So we're gonna do that every time. Every time we have to input like a new, every time we get a new reference, we kind of have to do that. But I guess that's something we have to deal with. So machine learning, GANs. Okay, so let's write about this guy. So introduced. So I kind of like writing in bullet points, or in like single sentences. So it was introduced by this guy. Why is this here? I don't know. And compiling is rather slow. Let's get rid of this. Open it again. Okay. The compiling is rather slow, and I think it's because of all the packages I'm using. I could probably get rid of most of them. So you need this. These are fonts, right? So you need these. These are fonts. This is math. Hey, Weber. What's your screen res? Is it bad? Is it bad, or is it like, why? Is there any question you're asking in particular? Because I had some trouble with the quality of the stream, but you can read my text, right? I think my screen res is 1920 by 1080, so it's 1080p. I'm working on an external monitor, so I'm not working on my Mac. I'm just working, like, my Mac's here next to me. I use the camera from my MacBook. So thank you for joining in today, or this evening. Hope you guys are having a great evening. So we need fonts, of course. We need math. We need math fonts as well. Set space. I think I use set space to define the distance between the paragraphs, but we can try to disable that for 1 second right now. So distance between paragraphs, because I don't like having like a new line break. I don't like it when text is like this. So you have like line, 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 and then the next line is a line, line, line. I don't like that, but we have English, we have parskip. I don't recall what parskip is for. Afterpage, no idea. Framed. You can frame things. Nice fraction, I don't think I need that. Appendix, not right now. Graphics, I need that. Hyperref, I need that as well. Enumerate, of course. Table, xcolor, indicator function, cite, cite, cite. Book tabs for beautiful tabs. Subfig, not needed right now. Lipsum, not needed right now. I have 2 indicator font packages here, so let's just get rid of both of them because we don't need them at all as of yet. Book tabs, cleverref. Cleverref is a very nice package. Listings, not needed. Algorithm, not needed. Pseudocode, not needed. Placeins, not needed. Maybe actually we do. Math tools, need them. We can put these in the custom commands here. The ceiling and floor. Probably not gonna need them, but make font smaller, make centering table. Okay, let's keep that. Epigraph, you can use it for epic quotes. Math tools. I'm not sure what math tools is for, so let's Google that. What is math tools for? To enhance the appearance of something, probably math. Okay, so for those who haven't tuned into my other streams, I hope I have some regular viewers now. So we already streamed. Wait, I'm gonna open my Twitch page real quick. So we actually streamed for quite some time already, and we did a lot. So we programmed in a neural network from scratch, like a very standard single hidden layer feed-forward neural network with sigmoid activation layers. We trained that model using backpropagation, which was very easy to do. So Weber is asking, is Vim better than VS Code? Well, I'm not sure if Vim is necessarily like better than VS. I don't want to see my own stream. I want to watch. I want to click on these videos. I'm not necessarily sure if Vim is better in VS Code, but it depends on what you're proficient with, right? So I took the gamble to invest a lot of time in Vim, and I'm very glad I did. So like, you could say I'm a Vim advocate, but it does take a lot of effort. It does take quite some time to become adept at Vim. Okay, so it doesn't load. Like, my internet is too slow when I'm streaming. So there is this Vim Learning Curve. There's a funny image about the Vim Learning Curve, of course. So here we have classical. I think it's this one, right? So you have Notepad, if it decides to work with me. So you have Notepad, which is very flat, right? You have Pico, which is a bit more steep. Then you have Visual Studio, which is like a bell curve. And then you have Vim, which is extremely high, and then Emacs is just all over the place. So I actually use both Vim and Emacs. I started dabbling in Emacs because I really like the fact that you're able to write that work mode is such a developed thing. So that's why I like Emacs. I like Vim because I spend a lot of time in Vim. I spend a lot of time customizing it. Why? Because it's fun. And I'm very productive in it, I think. I mean, I still have to learn a lot about Vim, but I could say it's my main editor. Using Vim comes with the advantage of having it on most servers. So most Linux servers, if you like SSH into them, then you have a pretty good chance of having Vim in there. So if you're comfortable with the standard bindings, so there's always the one thing I type at the beginning of starting a Vim that I like the IMAP KJ escape. Oh, so I can't type KJ, of course. So KJ escape is my to-go bind because that's my muscle memory. I spam that every time I'm in like normal mode. I just don't have anything to do to spam KJ, which is like escape for me. So hello viewers. For those who haven't tuned in, we did one stream on neural networks, and then we spent the last 2 streams on GANs, and they turned out to be much more difficult. So I reasoned, like, if I already spent 12 hours and they haven't even programmed in a single GAN, I can imagine that there might be someone else with the same problem. So what I want to do here is I want to write a kind of, for every stream I do, or for every project we're doing, I kind of want to end up with kind of, I don't want to say a book chapter, but something that kind of resembles it closely, right? So someone who has no experience with GANs at all can read that chapter, read that kind of paper-ish thing, and then come to a good overview of like what a GAN is, but also at the same time like they can do the math. So they have the necessary steps and requirements to do the math. So it's going to be a mix of quite technical, but also at the same time quite high level. And of course, the main goal of the stream is to program in, so that you guys can see me program in the GAN in real time. We had a lot of fun doing that with a neural network stream, and that was very interesting. I can show that real quick. So this is the class of the neural network, but it is in the wrong folder because we are using the neural network for the GAN. But here you can see I typed, I think this is wrong. I mean, it's not wrong, so we know it's okay. So it's not wrong, but we use a different loss function. So in the first stream, we used a standard. I'm gonna make a new tab here. So if you go up, no wait, we go to cd00, and then we type Python main, and then we train the neural network. If we add some other, let's add some more training iterations here. Yeah, that's a bit too many, I think. Let's see, maybe make it 500,000, sure. So, no wait, I don't want this. So we wrote a neural network from scratch, and here we see that the network is training, right? So we only use 4 observations, so that's not a lot, and we had some good ideas on how to extend this model using either more observations, randomly generated data, using different kind of activation functions. But I think it's nice that we were able to program in like such a simple model from start to finish, completely from scratch, without any external libraries. Then I thought it was interesting in the second stream to start with GANs, with a Generative Adversarial Network. But as it turned out, that turned out to be actually significantly more difficult than we anticipated, or at least that I anticipated. I set aside like, okay, I do one stream on GANs, and I do another stream on style transfer, then I do another stream on something else. But we've spent the last 2 streams already on GANs, so we want to wrap it either up quickly, or we want to maybe put that project on hold and try another project. But I'm not really a fan of that because I want to finish what I started, right? So it's almost done training. You can see that the trading goes, the loss keeps going down. And here we see that this is the real one, so 0, 1, 1, 0. And here we predict 0, we predict 1, we predict 1, we predict 0. Then on the we also tried to have it predict out of sample, but that didn't work as we only trained the model on like 4 observations, right? Okay, so let's start thinking about GANs. I actually wrote quite a big, I don't want to say big, but we wrote quite some stuff about GANs. Let me see here. So yeah, let's open this one. We had notes, GAN notes. So, oh, this is the GAN notes. This is the org GAN mode. So that's here. So we had these nodes. So again, okay. So let's start with the very first thing. So they were introduced by Ian Goodfellow et al. in 2014. That's just a simple fact. And they have become widely used. They have very interesting applications in, now I'm going to look at the GAN tutorial with SpongeBob, I think. He gave some cool examples. So, okay, so GAN, okay, so this is kind of not really interesting to me, but so GANs have become very popular and ubiquitous. Did I spell that correctly? Ubiquitous. I feel like that's wrong, but ubiquitous. Ubiquitous. It's wrong, right? No, I spelled it correctly. Oh, okay. That's cool. And so I have to find sources for this, right? Because this is not the main thing I want to discuss right now. Okay, so GANs have become very popular, blah, blah, blah. They're a cool model, but we're not interested in that. So this is what I don't like. This is what I don't like. So I don't like it when I have a line break here, but the line break here is not there. So what I want to do right now is I want to look at parskip. If I type in parskip, I can probably get some file that I used where I changed the parskip a bit. LR test. Was that use package parskip? So I think we parskip. All right, set space. We need those. File updated. Okay, good. So that is the parskip package that changes that makes become what is it called? New lines. I'm gonna type in like single sentences and I'm gonna try to keep them as short as possible. The worst thing I hate, the worst thing there is to me personally is like extremely long paragraphs of uninterrupted text. I don't know, my attention span, I have the attention span of a goldfish. So if you're reading like an extremely difficult technical text, right? You don't want like lines and lines and lines and lines without any breaks for your brain. But the point is that research papers are like that. So that's kind of a shame. Okay, so if we're going to think about what is the core essence of a GAN, what is the core essence of a GAN? I wrote that down somewhere. I think I wrote that down here. Not here, but in a GAN project. So what is the core essence of a GAN? GAN nodes, org, no, we want neural net, no, we want the README. Yes, so here. So what are GANs? So I made this during the stream. And what we see here is that I can put this on the other side maybe. Might be easier for you guys to see. So GANs are a class of AI algorithms, and they work on unsupervised machine learning. I'm not sure why I wrote it down here, because I'm pretty sure it's actually supervised machine learning. It's not unsupervised, so it should be supervised, actually. So you guys know the difference between supervised and unsupervised, right? So this is the key to a GAN. So this is the key to a GAN. So the key concept of a generative adversarial network, or a GAN for short, is letting two machine learning algorithms fight it out. That is, to me, I think, the key concept of what a GAN is. Can I zoom in here somewhere? Where is my toolbar? View. Show toolbar. Nope. Show toggle toolbar. There we are. So yeah, I think that is the key to what a GAN is. I think actually that the concept of I think that the key concept goes further than this. So I think it's a very important thing that we have to keep in mind. So GANs, like the N in GAN stands for network. So that means that we are using neural networks. But that doesn't necessarily that doesn't exclude us from using other algorithms, right? So we're not restricted to just using neural networks. So what ingredients do we have? So what are the ingredients? What are the ingredients of a GAN? Let's itemize. And now I press F5 and I get this easy, in Vim it then automatically expands to this. So, no, I think I need enumerate actually. Enumerate. What do we need? So, of course, we need training data. And that consists of, we have features and labels. Let's call the features X and the labels Y. I'm going to omit kind of a vector notation, but these are vectors, and a Y is most likely like a single number or scalar. So we have training data. What else do we need? We have, I think I wrote that down as here as well. We have the generator network, and we have the discriminator network. So we have the generative network. So that is, the generative network is the one that like gives the name generative to the adversarial network, right? So this network is going to create the fake data. This is going to create the fake data. Which, if you don't know what I mean with the fake data, I'll get back to you later. So then the second network we have the discriminative network, which separates real data from fake data. Very cool. Then finally, that's actually basically it, right? That is all we need. We need a generative network, and we need a discriminative network, and we need training data. Yeah. So, can we think of a nice analogy? So, a nice analogy for a GAN. Actually, okay, I'm gonna give credit where credit is due. We got this from the original paper here. Where's the original paper? So we downloaded the original GAN paper, which is this one, and we read it completely in one stream that we did. So we completely went through the paper, and here we saw that. So what it's saying here is that in the proposed adversarial nets, the generative model is pitted against an adversary. A discriminative model that learns to determine whether the sample is from the model distribution or the data distribution. So that is what we are going to do. We're going to create a model that generates data, and we're going to create a model that separates data from the real, from the fake data. So a nice analogy, I think, which was really nice, what they said here was, the generative model can be thought of as a team of counterfeiters. So is that of counterfeiting money. The generative model can be thought of as money counterfeiters, that produce fake money. And the discriminative model can be thought of as the police. We lift this straight from the paper. So competition in this game drives both teams to improve their methods. So competition in this game improves both the counterfeiters' ability to make fake money and the discriminators and the police's ability to separate fake money, fake currency from real currency. I'm going to add the word GAN to our add GAN to word list. So that is the main idea behind a GAN. If you have any questions about GANs or if you missed one of my streams, feel free to send a message in the chat, and I'm happy to explain it again because that is useful for both of us, right? So we're going to write, and in this case, we take both the models to be multi-layer perceptrons, so just standard neural networks. The discriminative model is also a neural network, and we refer to this as adversarial net. So adversarial nets is kind of a special case where both the models are neural networks, and we can train them using backpropagation and dropout. So here's some related work which we deemed uninteresting, which it's not, but we thought it was uninteresting. Okay, so now we're going to come to the math, and before I want to hop into the math, I want to give a quick overview again by giving you guys an image of what a GAN is. I think we made a beautiful image here somewhere. If I can show you this, guys, you can barely see it, but so this is a PDF. This is a PSD image that we did. Okay, maybe I'll just lift one from some paper. A GAN. So what is a GAN model? We go to images. So we had I think this one is I like this. I like this image, and there was another one that I really liked. I can't find it right now here, but this is a nice image. I think this is a very good image of what a GAN is. So mlbook, type gans.png, then we're going to include image that. I have some boilerplate, include graphics. Oops. So we can take this. To graphics, width is images, then we take GAN, caption, figure is a GAN schema. All right. And then we can take the mlbook, I'm gonna put it in images. GANs. All right. And now we should have a figure. We can type cref fig GAN. And we should have a nice image in there. No. Figure what? Oh, maybe it's here. Yeah, it's here. So there's one of my pet peeves with the LaTeX is all the imagery. So what did we do? Introduced by Ian Goodfellow, very popular, blah, blah, blah. The key concept is letting them fight against each other, right? So what do we need? We need training data. We need a model G, which is called G often. And we need a discriminative model, which is called D. The analogy is that of counterfeiting money, where the generative model is making fake money and the discriminative model is trying to separate fake money from the real money. Competition, so trading, improves both of them. So the generative model becomes better and the discriminative model becomes better and better as well. In figure 1, we have a schematic overview of a GAN. What is the source, by the way? I have to look that up later. So figure 1 gives a schematic overview of what the GAN is. So the random noise here is actually actual random noise. So we just generate, so the random noise, random noise is used as inputs to the generator, which we often call G, just to make it shorter. This random noise is not exactly random. We impose some prior on that. So we impose a prior on that. This is kind of from Bayesian statistics, where you say, okay, I have an idea of what the data should look like, and then I'm going to update it with the data that I see. So, I'm going to have an idea of what the parameter I think looks like. So you give a prior distribution, and then you update that with the likelihood of the data that you actually observe. In this case, we have random noise, but we draw it from a certain distribution. Often it's like a normal distribution that you kind of estimate using the training set. So often this prior distribution of the random noise is found using the training set. So random noise is then thrown in the generator to make fake data. Then the training set and the fake data, then the training set, then in the next step, the training set has features XY, but we're going to give the label to that fake, real, sorry. So the training set gets the label real, and the faked generated data set gets the label fake, say 0. The discriminative model then tries to separate the fake generated images from the real images. So that is the key idea here. So like this is it, guys. This is a GAN, nothing more, nothing less. Like this is it. Like GANs have become so kind of buzzwordy, right? But this is it. There's nothing more to it. You have three things. You have data that you want to model, that you want to create a model of, where you can generate new data from that. Then we have a model called G, which creates fake data, and you have a model D that separates fake data from real data. So yeah, that is it. What we now need. So that is kind of the overview in words of what a GAN is, and then we're missing one step. So we are gonna train. We're gonna have to train the model. Okay. So now that we have all that, we have to train the model. This training is done sequentially. So when the generative model is being trained, the weights of the discriminative model are kept fixed, and vice versa. If the discriminative model is being trained, the weights of the generator model are being fixed. So already I'm gonna discriminate. So already I have this like stupid extensions. Wait, okay, so I'm gonna. It's called like maybe a stupid extension. So I had this idea where maybe it's possible to use the same model for both the model D and the model G. So and then you like sharing the same set of weights. So this is one of my stupid ideas that is probably completely stupid, but I'm just like throwing it out there because in our neural network stream we figured out that you can generate fake data using neural networks by turning it upside down. So instead of using features to get input, you can just flip it upside down like 180 degrees, and then you get another. Then you can like if you then put in a label, you can actually generate the features back. So I was thinking while we're using two like neural nets here and here, why don't we just share them, right? Like, might it be interesting to look at the shared case? Because then then what happens is that you have the same weight. So the same weights are being used to both generate the model and discriminate the model. So I'm just really curious if that might work, right? Because what you then can do is because you train them in sequence, you can keep the weights of this one fixed and you update these, right? But these were your old weights. So then if you keep then you plop this back in here and then you train this, and then you might sequentially get to some equilibrium. But I mean, I'm just rambling on here. It was just a silly idea that might be interesting for future research. Of course. Okay. So we have this. Okay, so this is the main idea. If you have any questions about a GAN, what a GAN is, like about if you need any high level overview of what a GAN is, please stop me now in the chat. Because I've been over this GAN stuff like 20 times already in the past couple of streams. I'm more than willing to explain it again because I like explaining stuff. But so if we're done with this, we're gonna get into the math, which is a bit more difficult. I'm gonna try and make it as clear as possible as I can, but if I lose some of you, just let me know, and I'll be happy to explain everything all over again. We had another. I think we had another example. No, I think the police example is the best example. Okay, so yeah, let's get to the mathy part, which I kind of like, admittedly, because I'm a math nerd, right? I'm a math buff. So let's get to the math part. So we need a lot of things here, like to write down this model properly. We need a lot of things. Let's put this up a little bit, put this up here, and then we make this a bit small. I have keybinds for this. Make this a bit smaller, put it here, put this over here. All right. So, okay, these are the things we need. In our stream, we dissected these 5 lines, and it turned out that it contains a lot of information in 5 lines. So we're gonna pick this apart again. So what are the ingredients of an adversarial net? And in this particular case, adversarial nets, right? Because this is not. So what I just explained was more like the general GAN, but this is the adversarial nets where we have 2 neural networks competing, and we don't have any other difficult any other stuff. So itemize. We have element PG. I'm just gonna first write down all the elements I see. We have X. We have PZZ. I'm going to be sloppy here. Am I gonna be sloppy? No, I'm not gonna be sloppy. Now, how do you do math? Like, how do you math BF? Backslash X, backslash Z. So I'm gonna make that math BB, I guess. So Z, X, and Z. Yeah. Then we see the next parameter is gz dot comma theta g. So we have g as a function. Then let's be complete, and we have theta g. Then we have d. And then we have, of course, theta d as well. Then we have PG, which we did. We trained D to maximize the probability of... Okay, I'm going to go into those later. So these are all the elements we need to make a GAN. To make an adversarial net GAN. I kind of messed this up here. Okay, so that's a funny... math BBX. Oh, oops. Right? Should be this. What? That's crazy. Just gonna quickly Google this. Math BBX. How to make a bold X. Okay, that was very useless. So bold X LaTeX. A message as bold symbol, PMB, BM. Backslash BM and then use package BM. BM. Okay, so use package BM. So hopefully there won't be bold symbols might conflict with AMS math. Not math BB, but BM, right? Okay, let's see how many errors we get this time. We get none, and it seems to work. I do note I forgot something here. I forgot closing parentheses. Okay, so we made a list of all the adversarial. We made a list of all the things we need to make a GAN. And now I'm going to explain one by one what all of these things are. So so let's start with PG. PG is the generator's distribution over the data. And what exactly do we mean with the generator's distribution over the data? I think I'm gonna make a quick. I think I kind of want to make a quick image for you guys. I used ticks. I used ticks once, I think, to make this. Is this a badass thing? Much longer node. I use ticks, and you can make like beautiful things with it. Relax. Well, thank you. Bagging boost. Oh, come on. Bagging boosting. Takes 2. What's this? I made this? Awesome. So this is exactly what I need. I made this. I don't know when, but Tix has very nice. You can do a lot of nice things with it. This is actually also machine learning. This is something called bagging and boosting, which can be basically applied to any machine learning algorithm, where you first train on weak samples, and then you kind of like try to predict on difficult to predict samples more and more and more. So backing and boosting, that was this one. I'm gonna open this real quick. These are machine learning slides. We made a presentation over here. Then we did a node label. Then we have this. I'm gonna copy this real quick, and I am going to paste it in the ticks folder. All right. Then we have, so I'm gonna have to take a quick peek inside because I completely forgot how I use ticks. So we set a lot of nodes, backing boosting, nodes, then we M1, B1, M3, these are the names, I think. Below of this, right of this, below of this, right of this, below of this, right of this. And also, yeah, so first you define all the nodes, step 1. Then in step 2 you draw the links between the nodes. I'm very happy I did this. I think you have like draw paths from B1 and M1. So path this to here, this to here, this to here, etc., etc. Okay, so I'm gonna do this later. I'm not gonna annoy you guys with this now. But the generator's distribution over the data, I am going to open my Photoshop, where we yesterday we made a very big, we made a very nice. Okay, it's nice, but it turned out to be a bit convoluted in the end. We made a very big image in Photoshop, explaining what GANs are. So I'm gonna open that up real quick, and I'm gonna show you guys what we mean with the distribution over the data. So if I can zoom in here, if I can zoom in here. So this is what we sometimes do on the stream. I like to draw for you guys. So if you see this image the first time, right, it seems extremely chaotic, but we built it up slowly over time. I don't have my drawing tablet out right now, so I can't redo it. But the main idea is that the generator has some distribution, which is PG, and what you want to learn is the distribution over the training data. Like the training data has a certain distribution, and you want the generator to learn that distribution, and that is what we call PG. So that is what we call PG. PG is the distribution. So PG is the PG is the distribution of the generator. All right. Then we have X. So X in this case, if we go back to the image here, X is just the training data. X is just the data. X is a series of just a vector of I don't know how many rows, can be matrix, like it has, let's say, n observations and k features. So X is just the features, the data. So it has labels and features. Yeah. So PZZ is the prior distribution of the noise, of the random noise. So if this is your first time seeing GANs, I'm happy to explain everything all over again, because it might seem very confusing here, but the idea is very simple. So the idea is that we generate noise and we put it in the generator, and the generator makes some fake data from that. But we don't just draw any random noise. No, we put a prior on that noise. So we put a prior probability distribution of what we think the noise is. So I'm going to hide this again. So PZ is the prior distribution, or just the probability, is the prior probability distribution of the randomly generated noise that we put in the generator. All right. So that's that. Then we have GZ. So GZ is the generator. This is the generator. The generator is a function that takes in random noise, which is generated by PZZ, and is parameterized by theta G, and spits out features, fake data, fake trading data. Let's call it wiggle X, or we could call it X fake, but it spits out new values of X. It spits out new values of X and Y. Most likely X, but also Y. And hopefully, so the idea here is that we are able to change the parameters theta G by training the model, such that the fake training data becomes very close to the real data X. So that is the idea. So all the images you see like generated on all the images that you see generated on the internet with machine learning are most likely built by these kind of generative frameworks where you try to get as close as possible to the training data. So getting high quality training data is also quite important, right? All right, so theta G are the parameters. Theta is the parameters of the generator. I didn't capitalize this. So because the generator is a neural network, in this case, these are simply the weights and the biases. Then similarly, dx is also called the discriminator, and the discriminator is a function that takes in features, so it takes in features x, fake or real, and is parameterized by theta d, and spits out a number that indicates the probability that the image is indeed real. EA, it comes from the training data instead of the generator, instead of being generated by the generator. And then because the discriminator, so these are theta G are the parameters of the discriminator, theta D. And again, because both these models are neural networks, these parameters are the weights and the biases. Awesome. So we just wrote 2 pages about GANs. If anyone has any questions, feel free to answer them in the chat. Post them in the chat. I'll try to answer them as soon as I can. So these are all the ingredients we need. So we have. Okay, so this is not a parameter, but we're trying to learn this one, right? So we don't have to do anything for these as well. We do need to put in work for the prior probability distribution. So we need to put in work in something. So things that we have to do is we have to choose a prior probability distribution. We have to choose the functional form for the generator. We have to use the functional form for the discriminator. And of course, we have to train the model. And training the model is something we'll get into in a second. So here's something else. That came from the data rather than PG. In other words, players D and G maximize the following two-player min-max game. This formula seems quite difficult, but it's not that difficult actually. So the inner loop maximizes is the discriminator that first tries to separate the fake from the real data, and then in the outer loop, the generator tries to update its parameters such that it minimizes the probability of being caught. I don't really like this formulation because I think it's more like of an iterative procedure, right? So first you update. So given the generated data, D tries to maximize getting his chances of getting it right, and then given that, G tries to optimize his chances of fooling the discriminator. So we are going to write down a couple of things here, some other notes, because we are going to write down what this means. So this is like this has a particular interpretation. So log 1 minus d g z, and then if we're going to be really precise here, G is indexed by theta G, and this is indexed by theta D. So what this is we have, so if we put in, we train G to minimize this. So G puts in fake data Z, it generates a fake sample G, then it gives that to D, and D is the probability of it being real. So what it's doing, so if probability D is being real, then 1 minus is the probability of being fake. So it is it's minimizing the probability of being caught, which is kind of the same as maximizing the probability of kind of fooling the discriminator, right? So this is the log probability of fooling the discriminator. Is it though? So this is the log probability of where D as a number is the probability that it's real. So 1 minus its probability that it's fake. So it's a log probability of it minimizes the log probability of P fake. So this is the thing that the generator minimizes the log probability of being fake, in other words, being caught. And then we have and then we train D to maximize the probability of assigning the correct label. So we want D to maximize the probability of assigning the correct label to both the training samples and the samples from G. So that is what it's doing here. So it maximizes log dx. So log dx is the discriminator maximizes the probability of assigning the correct label to both fake and real data. So it's not necessarily that it because of course it can, what you could also say is, okay, well, the discriminator can just always say, well, this is fake, and then of course it always captures all of the counterfeiters, but then it stops also the actual good guys. Yeah. So if there are any questions, feel free to post them in the chat. I will try to get back to you as soon as I can. So if we're gonna be extremely correct, then here should be like theta d in as well, right? Because this is the discriminator. And depending if we keep, so there's no theta g in here because we assumed it fixed. All right. So then they play this kind of game. They play a min-max game. I'm gonna have to Google what a min-max game is again. So min-max game. If you like this content or if you want to follow me, feel free to follow me. Yeah, I apologize for streaming so late. Usually I stream a bit earlier, but due to personal circumstances, I was unable to do so. And I have to admit, I'm a bit slower. I'm a bit slower in the evening, so I'm more on point. I'm more on point in the morning. All right. So min-max game. Okay, so both players try to screw the other over, basically. Okay, I mean it doesn't matter that much, right? But they play a min-max game where they try to kind of screw each other over. So what do we have so far? Would this be understandable for someone who has never ever read something about GANs in their life? Would it be understandable? So we start by saying GANs introduced by this guy. GANs have become popular. Then we explain the key concept of what a GAN is. So the key concept of adversarial learning is letting two algorithms pitted on against each other. So what do we need? We need data, we need a gen, and we need a model D. We give an analogy of counterfeiting money. So the generative model can be seen as counterfeiters, and the discriminative model can be seen as the police, right? So then we have figure 1, gives an overview. So figure 1, random noise is used as inputs in the generator. Then this random noise is not exactly random. We impose a prior on that. Okay, that's true. Then often as prior distribution of random noise is found using the training set, sure. Then random noise is then thrown into the generator to make fake data. Then in the next step, the training set gets the label real 1, and the fake generated data set gets the label fake 0. The discriminative model then tries to separate the fake generated images from the real images. So that is everything. Then we have to train the model. Training is done sequentially. With the generative model is being trained, the weights of model D are being kept fixed, and vice versa. If the discriminative model is being trained, then the weights of the generator model are being fixed. All right. So here we're gonna go to the more mathy part, right? Because we need a bit of math to kind of formally write down and explain what we have here. So we have PG. So PG is the probability distribution of the generator's data, and we want to get this as close as we can to the distribution of the training data. Yeah, so the goal is to get PG. So the probability distribution of the training data. The goal is to get this as close as possible to the distribution of the training data. X, right? That is the goal. Then I kind of wanna remove this here. Maybe write generator not with a capital, but all right. So let's make that let's change that, change that, change that. Discriminator. All right, let's change that. Change that, and let's change that, and change that as well. All right. Yeah. So I mean, to me it sounds understandable, but I mean I've spent quite some hours already trying to debug and trying to figure out what GANs are. So if it's not clear, please let me know, and I will try to explain it again. All right. Then, so we did this. That's nice. Then we came to this kind of value. So this value function. I mean, it's yeah. I mean, I don't know if I need to write this down. All right. So instead of alternating, so okay. Early learning. So there is one issue. So one issue that might arise is that early on, G might not be able to learn well, because if the generator is so bad, then the training set is always able to. So, okay, so one issue we might run into is early on in training. If model D is so good, when model D is really good, and model G is rather bad, if the discriminative model is rather good in comparison with the generative model, then it has no trouble picking out the fake data from the real data, not giving the generative model an opportunity to train. So in that case, log 1 minus dg saturates, which we don't want. Rather than training G to minimize this, so the solution to this is to, instead of letting the generative model minimize the probability of being caught, log 1 minus dgz, we train the generative model to maximize log dgz. Which is, of course, the probability of generating a real image. So we maximize the probability of generating a real image. So yeah. So it has, so one of my gripes actually was, so why don't we just do this always, right? But okay. All right. Then here we have a nice like a nice image. Well, it depends on what you deem it nice. But this is an image. So the black line is the data, the green line is the generated data, and the blue line is the discriminator. And we see that it kind of so okay, so I'm not sure if I want to copy paste this in the paper, but yeah, so what you see here is that you generate samples, so you generate noise from Z, you put it in X, and X, that generates a green distribution like PG. That is PG. And the distribution generated by the black dots is the distribution of the data. And you see that if we train the model sufficiently, then PG becomes the same as the training data. And that is exactly what you want. That is the ultimate, this is the best fit, right? So then the discriminator is not able to distinguish the fake from the real data anymore. But here it is. Here it can say, okay, so this is most likely real, and this is most likely fake. Real, probability of being real is high, probability of being real is very low. Should I write that down? probably. Excuse me. Oh, sorry. I'm starting to get a bit tired here. I think I will stream tomorrow morning, early on, maybe starting at 7, and get back into coding the Generative Adversarial Network. I'm really passionate about that at the moment. Well, passionate is maybe the wrong word, but I really want that project to finish, right? So if you have any questions about machine learning or whatever, or if you're interested in machine learning, just let me know in the chat. Or if you just want to chat and hang out, it's also fine. Or if you maybe have some suggestions of what you'd like me to see me do, right? Maybe some sort of algorithm that you want to have explained, or if you need help with statistics or linear algebra, I'm always glad to help because I like helping people a lot. So what were we doing? We were writing a bit about GANs, right? We're understanding what GANs are, what they do, and how we can use them. And then we were going to write a quick user manual here. We did this already. We already wrote like 2.5 pages. We took out all the elements. We took out all the ingredients, both in math and in words. And now we are arriving at kind of the value function. We're not going to do theoretical results, but I am going to talk about I think I am going to talk about this image because I think the image is kind of insightful. All right, so let's name that GAN2. GAN2. All right. So this is another. This is kind of a training of a GAN. So CREF figure GAN2 shows a schematic overview of what a training of a GAN looks like. So random noise. So random noise is generated. Random noise Z is generated. The generator G, Z, theta. The generator theta G then turns this into features X, which kind of I think it's in there, which maps X is GZ. So that turns it into features. So X is GZ, and this imposes a distribution PG. So that is the PG. So the PG, so the imposed distribution is PG, the green line. The real data is denoted by the black dots, the distribution of the data. The discriminative model, model, I guess. The discriminative model is indicated by the blue dash line. Taking in values of X and returning a probability of the data coming from the real distribution rather than the than PG, right? So that is the main idea. That is a kind of a sort of a visual image of a GAN. So did I write this down? Yeah, Fig2 GAN. So Figure 2 shows a schematic over. Look, already I'm turning into like having long sentences here. So Figure 2 shows a schematic overview of what trading a GAN looks like. Random noise Z is generated. I'm gonna turn this into maybe 1 even. Random noise is generated. The generator GZ then turns this into features. X is GZ. This imposes a distribution PG, the green line. This creates a distribution of transformed samples. Indicated by the green line. The real data is denoted by black dots, the distribution of the data. The discriminative model is indicated by the blue dashed line, taking in values of X and returning a probability of the data coming from the real distribution rather than PG. So ultimately, so if the generated model is far away, if the generated distribution is far away from the distribution of the real data, then the discriminative model has an easy time picking apart the two. But if we look at scenario D, where the generated distribution overlaps exactly with the real distribution of the data, the discriminative model is unable to separate the two in any way, returning a half all the time. Because then it just doesn't know which one is real, which is fake. So we are perfectly, of course this will never happen, but theoretically it could, it should, and there is an equilibrium that supports this thing. All right. Any questions so far? Because this is basically what a GAN is, right? So this is it. Nothing more, nothing less. All that we have to do, all that is left is to explain this thing, but it's rather easy. And that's it. So that is a GAN. That is a GAN again. I'm not gonna talk about. So all we have to do is do the algorithm. Yeah, there are some theoretical results, but all that is left basically is to figure out this. So, and where do these two come from? These come from the these of course come from the fact that you are optimizing for the discriminator the probability of separating the two. So this is what you get. Wait, I can type these out. I will type these out. All right, here's some nice LaTeX showcasing. So let's make an align here. So we have shit. What's it called? Numbla, I think. The upside down delta. I think it's a numbla. No, it's not. A nubla. Maybe a nubla. Upside down delta. Nope. A nubla. Why is it? Nubla LaTeX. Not sure why I can't type nubla. AMS math. Oh, it is working. So we have nubla, then we have theta d, we have fraction 1 over m, sum I is 1 to m, then we have a left right, we have log d x I fat x plus log 1 minus d g z. Wait a second. Yeah, that's it. But I want to separate these two because I'm gonna give them under braces. Alright, there's that. I forgot the brackets here. And maybe I can even copy paste this and then remove then we can remove this part and we're done. And we can remove the left right as well. There we are. Alright, that was some quick LaTeX work. Is that, no, let's see, correct amount of braces. Yeah, so what do these things mean? So we can, if we maybe underbrace this, underbrace. Oh shit, that's gonna give an error, I think. Underbrace that. And we have here some text test. Alright, that works. And then we underbrace this, so underbrace with some other text. And we underbrace this as well, because why not? Sure. Alright, so this thing is, it's in the algorithm and we have to update the discriminator. So we're gonna change the parameter, and how we're gonna do that, we're gonna do that with the derivative of the loss function. So this is basically the derivative of the expected loss function here, where we just have the minibatch. So the derivative of this thing comes from the fact that we want to minimize. No, we want to maximize the probability of assigning the correct label. So D is the probability of assigning the correct label. We want to maximize the probability of assigning correct label. I'm not sure if it's going to wrap. I don't think it's going to wrap. I might have to wrap it myself, yeah. Max prob of assigning, maybe there's a space, assigning correct label. That did not work. Okay, is there any way to make a line break in an underbrace? How can I write multiple substack? Substack. All right. So Substack works. Probability of assigning. All right. Um, no, that did not work. Oh, okay, Substack and text. What am I doing wrong here? Oh, man, see, this is why why I should not code in the evening. So you have Substack. So you have underbrace. Okay, this should work. So you have a Substack with two text things in between. That is what you're looking for. All right. So we have the maximize the probability of assigning the correct label, both real and fake. And this is the so text here. This comes from the of the real data and the fake data, and that is the probability of being fooled, right? Yeah. So this is this comes from the probability of assigning a correct label to real data. Probability of assigning to real data, and this is the probability of giving. You have fake data, and then the probability of that being real, and the probability of that being fake. So let me see. Because that is like assigning the correct label to the real data. That is D. Plus the probability of assigning a fake. So here you wanna assign fake label to fake data. This is not entirely clear to me yet, to be honest. So I will have to so this is a kind of a loss function, right? But it's still kind of a bit vague to me. Because we actually wrote down something about this, right? We wrote down this here. We wrote down. So this is the discriminator maximizes the probability of assigning the correct label, both to fake and to real data. But in here we have the xi, where the xi comes from the real data, and the zi's come from the fake data. So if we go back to the loss function here, we see that so given given a set of given that there is fake data, then we try then the discriminator tries to maximize his parameters such that he maximizes the probability of this and the probability of this. But the probability of this is I think not being fooled, right? So this is the probability of assigning the correct label. This is the probability of assigning real to a fake image. So 1 minus that is the probability of not assigning real to a fake image. So not assigning real to fake image. So not assigning real to fake, and you want to assign real to real, basically. So that is where the loss function comes from. So if we look at the loss function here, so here we take the probability of assigning the correct label to the real data, x, right? And here we have not assigning a real label to fake imagery, because in here we put fake imagery, and we don't want to give it like a real label, right? Yeah, that kind of makes sense. Okay, so now it's clear. Huh. And then in here, excuse me. Oh, sorry to get tired of it. And then in here, what we have is we just maximize. I think we maximize the probability of not being caught, right? So, oh, this is by ascending. Update discriminator by ascending, and this is update discriminator by descending. So we kind of want to do minus this. Because the generator minimizes, right? So we want to minimize this. Or you want to maximize. I'm just gonna write max in front of this here. I'm gonna write min in front of this. So we want to minimize the probability of being caught, like so. Minimize p being caught, basically. That is. So you want to update the parameters to minimize the probability of being caught. Yeah. So the min-max is not entirely correct, but hey. So this is the algorithm. And I'm going to look whether I can find a nice copy here. So algorithm, LaTeX. If blah 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 begin for okay, so we use k as 1, so it doesn't even. So okay, we don't necessarily need this at all. Okay, so the training algorithm or sequence is as follows. Repeat. I kind of want to. So you iterate between these two steps, right? So the trading algorithm is as follows. You iterate between these steps until convergence or sufficient loss is achieved, or the amount of iteration steps is max amount of iteration steps is exceeded. So itemize, no, enumerate. So enumerate between like step 1 and step 2. So so enumerate between these two steps, and the first step is it's given an error for some reason. whatever. So the first step is training the discriminator. Second step is training the generator. And in this step, we do itemize. So we sample mini batch of size m. Sample a mini batch of size m, which looks like this. We sample a mini batch of m noise samples, Z1 through ZM from the noise prior, sure, which we discussed above already. Then we sample a mini batch of M real data examples. Let's call them, well, X1 to M. They should be L dots. I don't know why, like, yeah, to XM. So we first sample noise. So we're gonna train the generator now, right? So we're first gonna sample noise, and we're gonna sample training data. Then we're going to make fake data with that. So we are, okay, all right, so now I remember originally when reading the paper, I was very confused because I would expect now something along the lines of use the random noise samples to generate fake data. Okay, so upon first reading the paper, one might now expect a line of something like use the generated noise to create fake data using the generator. This line is missing, and this is because it is implicitly done. Oh man, I can't write. Implicitly done by invoking GZI, because that is exactly what the generator does. So if you're going to program this in, you're gonna need a function that is able to have noise as an input and output a fake image, or well, fake image, fake features, and in our case, it's an image. All right. So upon first reading the paper, one might now expect a line or something like, use the generated noise to create fake data using the generator. This line is missing, and this is because it's implicitly done by invoking GZI in the algorithm, in the gradient descent, or ascent actually. Then you update the weights of the discriminator, which are denoted by theta d, by ascending the stochastic gradient. So you basically update the weights using some particular formula, which we will get into later. So you train the discriminator, and you keep the weights of the generator fixed. And when you're going to update the weights of the generator, you're going to keep the weights of the discriminator fixed. So for the generator, it's actually easier because you just have to sample noise. Like you don't have to sample the real data actually. So you sample a mini batch, and then here you update the weights of the generator data G by descending the stochastic gradient. I'm not exactly sure why it's called a stochastic gradient here, but it's probably because you're taking the expected loss, because we're dealing with probability distributions now. When we programmed in the neural network, we did not have a stochastic loss because the loss was just like a squared error loss, right? But here the loss is an expected value, so probably that's why it's called a stochastic gradient, because the gradient is not like, well, fixed. So what they're saying is that gradient-based updates can use any gradient-based rule. Learning rule, we use momentum. Like, I don't know what momentum learning is. Momentum learning. Like, my intuition is that it uses kind of it kind of has like an exponential decay or something. I have no idea. Momentum learning gradient descent. Stochastic gradient descent with downwards momentum, or with momentum. A lot of things on machine learning is more getting used to the jargon than really understanding any real deep math, in my opinion. If you disagree, feel free to disagree, but that's just my opinion. All right, so this is a part 2. Blah blah blah. Stochastic gradient momentum, exponentially weighted average. So I already thought, like, wait a second. So momentum, which almost works better and faster. It helps accelerate gradients, thus leading to faster convergence. This is the one thing I hate about meeting. You cannot click anywhere, or you get sent to a silly. I just want to click around when I'm reading so I can have a bit of focus. But if you click, then suddenly you're on a new page. So here, momentum is a momentum accelerated gradients leading to faster convergence. One of the most popular algorithms, many studied art, blah 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 blah. Okay, so it's probably that you're gonna exponentially smooth the gradients you find and use that to take like a proper step in the good direction. So exponentially weighted average, sequence S, cosine function, add some noise, sure. Even though the dots seem close. You want some kind of moving average which would denoise the data by bringing it closer. Exponentially weighted average moment. So this is just an exponentially weighted average, I guess. I called it, didn't I? I swear to God, I called it so hard. You can look back in the stream, and it's just... Oh wait, this is exponentially weighted average. Never mind. That is exactly the definition. You can use beta. You're approximating over beta. Sure. Sure. Whatever. Bias corrected version. Okay, SCG. Okay, so here we can average over the gradients. So you provide two definitions, pretty similar. Define momentum, which is moving average of the gradients, but then we use it to update the weights of the networks. So here you use here you use the old gradients plus subfraction of the new gradients. So you so that is what they mean with you keep the momentum. Yeah. And the learning rate, of course. So here are your weights. So you descend your weights according to some parameter, and then you kind of use. Okay, so momentum learning. So in the paper, the word text BF momentum learning is mentioned. Momentum learning. Momentum learning refers to the fact of simply averaging out exponentially over the previous gradients, such that you kind of exponentially smooth out noise and hence use the momentum from the previous gradients to use in this current step. So imagine if all your gradients are kind of like this, then you keep following the trend, and one bad gradient or one gradient that is 0 is not necessarily gonna change the step you take by that much. Like if, for example, the gradient would be very small and you would not use momentum, then it might get stuck there, right? But if you use the momentum from the previous gradients, then it might go over that local minimum, minimum or maximum, and then come to maybe a better one. There's another one. There's a Nesterov, but I don't think I want to go into that necessarily. With momentum, without momentum, sure. Conclusion. This is this looks fine. So we kind of discussed everything, guys. Here's some optimality. Oh, they also in the paper also the word dropout is used. Oh yeah, also another jargon or term in the paper is that of what is it? Gaussian parsen window, which is just a fancy word for saying kernel estimation. Gaussian kernel estimation. So some people are pretty familiar with kernel estimation, right? But parsen window, I had no idea what it was. So the generator nets, the generative model used ReLU and sigmoid. The discriminative model uses max out activations. Dropout was also used. Dropout was applied in training the discriminator. All right. So then the theoretical framework permits the use of dropout and noise at intermediate layers, but we only use noise as the input to the bottommost layer of the generator network. Okay, we estimate the probability of the test set data under PG by fitting a Gaussian parsen window by the sample generated. So I don't understand this in all honesty. Like, I don't understand this sentence. Like, what is it used for? I think it's used, so this number is big, and it turns out that big is good. These numbers are big, which also turns out to be good. So stacked seed, so these are other models, right? So what they're saying is our model is the best, and our model is the best because they provide the highest log likelihood estimates, mean log likelihood sample and test set, standard errors across folds, different sigma, different validation set. So we compute log likelihoods. How do we compute log likelihoods? The probability of the test set. So you do a kernel density estimation on the samples generated with G and report the log likelihood under their distribution. Okay, so you train the model under the test set, and then with the samples generated from G, you do a kernel density estimation, and you report the log likelihood under this distribution. So this is just kind of a model, kind of a fit, like how well does the model fit. Excuse me. And here you can see the images that are being generated by the GAN, and hopefully we get to that as well. And it's really cool. Yeah, I think it's honestly really cool. So these are generated by the dataset, and they look kind of striking, right? Really cool stuff. Digits obtained by linearly interpolating. Here are some advantages, disadvantages. So yeah, if you have any questions, let me know in the chat. I'm happy to answer them. That's basically all there is to GANs. I've been streaming for 2 hours now, and I made this document in 2 hours, so that's 1 page per half hour. Usually I would do it faster, but yeah, I kind of hope I was able to kind of give a good overview. The last thing I'm going to do is I'm going to go to this guy's website, NumPy GAN. There was this guy who made a GAN that worked quite well, using only NumPy. And I'm gonna steal. Well, I want to say steal. I'm gonna be inspired by. I'm gonna use his equations to program in the GAN ourselves, because I tried deriving it manually, but once I saw his equations, it suddenly clicked. So these are the GANs that are generated from the simple GAN, which is really cool. Like it works. That's pretty awesome, right? So I won't be covering too much of the math. I did cover the math, and I don't know what atom optimizer is, but we'll see that. So these are the equations you need. He uses like rectified linear and then just a sigmoid activation for the second layer. And then he has like the cost function is minus this one and plus this one, which we have here. Down here. And then we have these are the kind of the chain rules that you need to update the model using backpropagation. Because if you only use neural networks, you can estimate the model using backpropagation. So you take the derivative of the cost function with respect to the parameters. And because of the log, of course, you get the 1 over. Then you have to take the derivative of this with respect to the sigmoid, which we see here. Then you have to take the respect of the derivative of this with respect to this here. No, with respect to dw2, so you get LAI. And if you take the d cost with respect to dw1, oh, but this is only for the discriminator. Then for I didn't scroll further. Oh, here's for the generator. Okay, I didn't look at them actually, to be honest. So I really was confused a bit. All right, so here's the GAN, right? So we're gonna need this. We're gonna need these as well. Layer 1, layer 2, layer 3, layer 4, layer 5, layer 6, layer 7. So that's a lot of layers. Is this Python? Yeah, it is. Huh. Nothing special. Training results. Training GANs is hard. So wow, there are a lot of parameters. 2 layers, 200 and 560. I think it's cool that it shows his bad results. How is the input factor size 100? I don't get that. Generator 10H. Whoa, look at that. That's cool. But what is the prior he's assuming? Alright, that's pretty cool. Maybe I should also write something for towards data science, you know? Who knows? Maybe it gets some exposure. And I don't know if that's even allowed or whatever. Contribute. Whew. Alright, so I hope someone tuned in today and wasn't aware of what GANs are, and hopefully is a bit more aware of what GANs are today. So I tried to convey what a GAN is. It's actually, the idea is very simple. Implementation and training is very hard, but the idea is very simple and a very powerful idea that so we needed a bit of math. In the end, if you do the math once or twice or 3 times, the math isn't that difficult anymore. The loss functions are a bit tricky. They still aren't that clear to me in my head. the training algorithm is actually quite easy as well. I mean, you first train you just mini-batch, then you train the discriminator and then the generator. Yeah, so if you have any questions, you can post them in the chat. I was glad to have you guys. I've been streaming for 2 hours. I'm getting a bit tired. I'm gonna brush my teeth and maybe watch some Netflix. So if you have any questions, the moment to post them is now. Otherwise, I want to thank you all for joining me on this late evening, and I hope you guys had a great time today. I hope I was able to learn someone something. And if you like my content, if you want to see more of me, please don't forget to follow, because it means a lot to me. I will be streaming more, and I won't be streaming this kind of content. I know this might be a bit boring, seeing someone read a paper and write about it. But like, I don't want to say I was bored, but I think streaming is nice because then it forces me to be clearer than if I weren't streaming, right? So if someone wants to tune me in and put me on like kind of like as a white noise or background noise, I still appreciate that a lot. So yeah, I think the kind of content that you will be seeing from me is me trying to program in all the algorithms. But of course, if you have to program them in, you kind of have to know what you're doing, right? So I could do that and prepare beforehand, but I don't think that would be like completely honest, because then I would not show the struggle that it takes to kind of really understand something. Because I spent now 2 hours. The second stream is like 6 hours, and then the third stream is also 6 hours. So that's like 12 plus 2 is like at least 14 hours trying to really understand what GANs are. And I mean, it takes some time, right? And I mean, that's time I'm willing to spend, because I think machine learning is extremely cool. At the one hand, like on the one hand, I think it's extremely cool. On the other hand, I think it's just kind of statistics. It's kind of buffed up statistics. It has a lot of media attention. I don't think it's AI or AGI, but yeah. So I think GANs are really cool. I hope I was able to learn someone something. If you like this, don't forget to follow. If you want to just say something, just hang out. Feel free to post something in the chat. I will probably be on tomorrow very early in the morning. So that's like, I don't know, 7 in the morning. And then I have stuff to do during the day, and I won't be back until late at night. So yeah. Thank you guys for tuning in. I'm gonna go now. If anyone wants me to, I can upload the document. I probably will upload the document. I will upload all the program files to a GitHub anyway, but I still have to learn how GitHub works a bit. So thank you guys for having me. I had a blast having you guys. Yeah, and hopefully I'll see you guys around.